thank all of you for being here. In particular, I want to just congratulate Dr. Turki on his leadership of KAXT, and I'm sure that he will apply the same intensity as always applied to his contribution to the vision of science both in Saudi Arabia and abroad. I think he's really I call him a natural resource for his contribution to the building science on a global scale. I also want to acknowledge the efforts of my colleagues here for nominating me for the prize, and it certainly is a huge honor for me and for my group and for the whole community that is doing MOF chemistry. I believe that our past determines in some ways our present and certainly gives an idea about what we are going to do in the future. And so what I'd like to do today is I want to start by giving you some idea about how I became interested in chemistry and how that has led me to the invention of these new materials. I don't really want to necessarily say this for my own satisfaction, but also because I discovered that the applications of these new materials are not only restricted to the energy and environment applications that were mentioned by Dr. Turki, but also they really have inspired people to think in a different way about making materials, and especially young scholars. And so I think that it is appropriate to take this opportunity to share with you some of the things that I have experienced as a child and how they have influenced my thinking, in the hope that someone out there will find this interesting, if not inspiring. I went to a school in Jordan, a private school, and usually we had a break at 10 minutes past 10 every day that we were in school. And during this time, the library was supposed to be closed, and so so I had to peer behind those closed doors to find out what is inside, and I came across drawings like these, and they really captivated my imagination. And then later I realized that they were molecules, and they were really the underlying construction of materials that we deal with every day. So this stayed with me, and but before that, it was really my fate that usually I have to walk, and this is a common story in our world, I had to walk 3 miles every day to school, just one way. In the middle of that journey, I would stop into my father's shop, either have breakfast, or on the way back, my father would prepare lunch. In the meantime, I would help him with whatever chores needed to be done at the shop. But one day, as I returned from in 9th grade, returned from school and stopped by my father's shop, he said, "You're going abroad to do your work, to continue your work." And I said, "But I haven't even gone to high school. I want to finish high school here. I want to finish college in Jordan. And then I'm not sure whether I really want to ever leave." And so he said, "No, you're leaving. And so you either go to the Soviet Union and study medicine paid for by the Communist Party, or you could go to America and work for your schooling." And you know, after a lot of arguments, in the end, I had no choice. So he pushed me onto this airplane, and I was shipped off to the United States. I chose the United States because we heard so much about how wonderful that country is. And there it is, KLM flight, my first time on a flight, and it was, I was 15 years old, and I found myself in the United States. And my father said, "When you get to the United States, I want you to go directly to school, to the university, and show them your grades from 9th grade. And I said, "Well, what about high school?" He said, "Forget about high school, just go to them and show them your grades." So I went there in broken English, and I said, "I want to enter the university." And they laughed, and I said, "But but I have no choice. I have to do it. And so at that time, I can enroll in an unmatriculated program, but take the same classes that the normal students do. And they said, if you do well, we have no choice but to admit you. And so I did well, and I was admitted. But this is the kind of scene that I arrived at. Party school, SUNY Albany. And to me, I was completely disconnected from this. I had just in my pocket my entire family savings in cash that I was supposed to spend on my education. And within 1 year, all my father's savings are gone, okay? They've been spent. And so I had to do various things, from working odd jobs to taking loans and so on, and to survive. But in the meantime, I was very keenly aware of the fact that I don't have much money, and that there was great expectations waiting for me in Jordan to pay back, perhaps, but my own obligation to pay back. But I really was immersed in research. I found myself working with 3 professors at 3 different projects at the same time. And one of them, later I learned, wrote in my recommendation letter for graduate school that I would make a great theoretician working on a computer. And so that's really the beginning. And at that university, I found a book, and in that, or a university catalog. Before the internet, we had catalogs that describe what professors are doing, and they would show drawings like this. But I saw this drawing, and without knowing what it is, I said, what a beautiful molecule. I think I'll work with that professor. That professor happens to be at the University of Illinois, and it was Walter Klemperer, and I said, okay, if he's a nice guy, I think I will go ahead and join his group, and if I can't join his group, then I can't go to that university. And sure enough, that's where I ended up, at the University of Illinois, Urbana, to study chemistry, PhD in chemistry. And there he gave me a task to deprotonate a molecule like the one that I was in love with there. All chemists know that deprotonation is one of the easiest reactions that anybody can carry out. It's a simple reaction. And so I tried to deprotonate this thing, and it wouldn't deprotonate. For a whole year, I could not get to the product that I was looking for. Then after a year, I realized that I may have done it. So I went to the NMR machine, I stuck my sample in the NMR machine, and there I found, I had already, for a whole year, I had predicted what the NMR spectrum should look like. And this NMR spectrum I found didn't look anything like what I was expecting. So now you can see that with all that traveling all the way to the United States, walking 3 miles a day every day when I was growing up, all of that came right in front of me saying, you are a complete failure, you're gonna be kicked out of graduate school. Okay, that's it. I'm not gonna have anything to talk about in my oral exam. So I went back to the lab, and I was extremely sad because I found that, in fact, that sample had even turned from that nice, brilliant orange color into this ugly brown color. So that even made me more depressed. So I turned around, and this story is very important for researchers. I turned around to the senior postdoc in our group, and I said, what do I do with this? Which every new student will do. And he said, Omar, that looks terrible, throw it away. Okay, it looks awful, he said, throw it away. So instead of throwing, it was late at night, instead of throwing it away, what I did is what all chemists do at some point in their life, and that is to take this brown gunk, separate it from the liquid, and redissolve it to do what is called recrystallization, or try to crystallize it. So I set up a crystallization. I went home and thinking that I'm a complete failure, and the next day I found beautiful, beautiful, brilliant, dark red crystals. Okay, so that, regardless of what they were, whether they were interesting or not, they were the love of my life because they were saving me, one, from failure, but also they were in the form that I always loved about chemistry, and that is these brilliant crystals that define the compound that you have made. They are also a way for nature, God, nature, to reveal itself to you through these crystals. It is really the secret that life is knocking on your door and saying, this is what you need to be learning, this is what you need to be looking at. And that's why crystals are really the dream of almost every synthetic chemist. Those crystals were in structure, when we determined their structure, were beautiful compound, as you can see here, ball-shaped compound. This compound I will not talk too much about. This is way long ago in my past, but it looks like a ball. It turned out that it goes around and traps molecules that have cyanide, like acetonitrile or nitrile ending to them, and it traps them in the pore. This was the first of its kind material ever made, and it's still a material that there's no other like it. It was really the beginning of what is called the polyoxoanion field. But this was all work that I was credited for, but this is my graduate work. It stayed in Illinois. But what stayed with me was the advice that my advisor gave me, or what I learned from my PhD advisor, my mentor. He said, science begins with doubt and questions. And to me, this is a very pessimistic view about things. But it is correct that science really begins when we start asking very hard questions and disputing our observations and why and our explanations. That's when the real thinking begins. Then I went to Harvard to do my postdoc, determined not to do anything with organic chemistry. For some reason, I did not want to do organic chemistry. And so I went to my advisor and I said, Dick, I don't want to do any organic chemistry. Do you have any inorganic projects? And so he pushed me away and said, you do whatever you want. And so what I did is I took solids of this kind, and the idea was that you would excise out of a solid a cluster as a molecule. So essentially taking a building block out of a cathedral or out of a building. And we called it excision, and that worked. And I got a paper, and then I reflected on what Dick has taught me. And Dick said, research is an exercise in optimism. So one guy tells you a pessimistic message, and the other guy tells you an optimistic message. And here you are stuck in the middle, trying to figure out what's going on. And I always say to students now is that don't necessarily choose, but do consider these things when you are thinking about how to articulate your own thinking. Just simply by considering them, you will come up with your own idea. So mentoring is a very, very important part of doing research. And also, I think you can appreciate that mentoring is also a very reliable way of sustaining innovations and excellence in research. It is really one of the components that we are collaborating on here with KEX. There is as mentioned by Dr. Munir, we have a KEX Berkeley center where scholars can go back and forth and interact with scientists on both sides. So I'm very proud that we have this center, and I have great hopes of achieving something great through the center. Okay, so I I had a choice of going to industry, to AT&T Bell Labs, or to Arizona State University. The salary was 3 times as much as at AT&T. So I accepted the job at Arizona State University, and for $38K instead of the $80K or so that I would have gotten at AT&T. Again, the love of molecules, and not necessarily the socioeconomic background that I had, was a much more important driving force for me to maintain my interest in doing science. At Arizona State University, the real work really began, and that is that you are now on your own. You have a lab, and you have never been taught how to start a lab, never been taught how to supervise anybody really, and you have to come up with your own ideas. In those days, it was a matter of pride that you come up with your own ideas. And so I looked around and I found that, in fact, if you look at all great materials of the 20th century, you find that they're either inorganic or organic. So let me share some of those with you. So for example, petroleum. Every drop of gasoline goes through a zeolite like this. It's known as a mineral, and the reason we can use it today in refining petroleum is because some scientists in Union Carbide was able to synthesize that in the lab, and now it's made in multi-ton quantities and it's used in refining petroleum. Silicon is another very important material. It's used in computer chips and has transformed the way we communicate, transformed the way we compute. Aerospace materials, they're largely inorganic. And certainly without robust materials and reliable materials, we wouldn't be able to go from San Francisco to Riyadh in the short time that I did yesterday, and in the reliability that aviation has. Plastics, organic compounds, they transform the way we package things. They transformed almost every aspect of our life and made living well an affordable option. Pharmaceuticals, they're organic, and without them, we would have a lot of problems. They have certainly contributed to our quality of life. So these materials define the 20th century development of large economies, and certainly they are molecular and they are either organic or inorganic. I should not neglect to say that steel and concrete are very important materials, and without them we would not be able to build beautiful monuments reaching the sky and inspiring us. So, as I said, this is either inorganic world or organic world. And so I wanted to change that. I wanted to make a world that made from inorganic and organic, because inorganic provides you robustness and other important properties. Organic provides you with a flexibility of tailor-making your material for a very specific property. And if we are to transform the 21st century, as those materials have transformed the 20th century, we needed materials in which we can precisely design their composition, precisely pin down molecules exactly where we want them, and that's exactly what we did. We started thinking about. We didn't do this right away. In the meantime, I was really shocked at how we make solid-state materials. We should make them by shake and bake. And that means you take two components together, mix them up, heat them up, and see what you get. There was no design involved, and that's just how, when I was a student and before, that's how people made solid-state materials. So I wanted to change that, and here the idea was that if you want to combine organic and inorganic, the inorganic can give you a way to design intersections, while the organic can give you ways of connecting them. And so that was the idea. And it took a few years, and I can give actually 2 lectures on the discovery of this compound that I will share with you now, but I won't today, but only to say that we were very fortunate to be able to make the first metal organic frameworks from very simple materials. The main component of plastics is a terephthalate, and the main component of sunscreen is zinc oxide, to make a wide variety of materials. In those days, we called them metal organic frameworks, and now people call them MOFs, and we gave them a number to give roughly in chronological order of discovery. The yellow ball you see there is to illustrate the space within the structure. So here, in one step, you're able to take rigid building units and link them together. These are zinc oxide units, and link them together through organic units and make a crystalline material. Now, everyone before this tried to do this, and all you get is junk, like that brown junk that I showed you, or things that are not characterized. And so we were very successful over a 3-year period to figure out the system and make it work. And so persistent worked. Persistent finally paid off. These are the crystals that you see if you make MOF5. They are truly inspiring, very beautiful crystals. It was then very easy for us to, after that, to crystallize anything else we want with a different organic link and also use longer links to expand the pores. Prior to this, no one has ever been able to do this in solid state materials, and so we were showing how this could be done. And once you have figured out how to do one or two of these, then it can be applied on almost every organic molecule that you can functionalize with carboxylate and every inorganic cluster. And so there are thousands and thousands of possibilities, and so we have certainly opened a gold mine. And just to give you an idea, here we are linking triangles and squares to make a beautiful extended structure that is a star now in methane storage. Here we are linking triangles. I won't describe these structures, but here we're linking squares. So it's almost like molecular tinker toy chemistry. Linking trigonal prisms and linking trigonal prisms to make magnificent structures. Linking of cube octahedra. I like to show this because when we started doing this work, people say, oh, well, these things would never be stable. They're mostly organic. They'll burn up. They will dissolve. They will do all kinds of things. And then, of course, we proved that they're thermally stable. In this example here, this material you can boil in acid, you can boil in base, you can keep it in water, nothing happens to it. It's a robust material. But yet it has organic components and inorganic components. So we're looking at the emergence of completely new kind of materials that will dominate, I think, this century. Just to show you how fortunate we were in that basement at Arizona State University, we were able to make zeolites. Now, I mentioned zeolites before as one of the most important materials in the last century for refining petroleum, but you can make MOFs that are based on these very structures, these very special tetrahedral structures that are based on minerals. They're based on the silicon-oxygen-silicon angle with two tetrahedra of silicon linked together into extended structures. And our idea was to make MOFs out of them. We called zeolitic imidazolate frameworks by linking transition metals with imidazole to make that linkage. Again, this is an 80-year-old challenge. How do you make zeolites metal organic? And now with just this idea, it took us about 4 years to make this work, but once you make it works for everything. So this is one of the structures of ZIFs. It's known here as a silicate, and in this case, you see it as one of the cages as a ZIF. So not only can you link this entity, but also any entity, functionalized or otherwise, can be linked as long as you have those two nitrogens in the position that I mentioned before, as you can see here. And so we did the high throughput synthesis to search for all the possible structures, and again, my love for crystals. Here are some of the crystals that you see in those wells. And in just one experiment involving about 10,000 reactions, we discovered 25 different structures. And these are, I'm going to just show a movie of them. You can see these are all based on zeolite type structures that are made from metal organic. We can make them from almost any kind of link, polar, non-polar, mixed links. The metal can change from zinc to cobalt and others at this time. We made some of the most important zeolites as metal organics, as you can see here. This is sodalite, which is a silicate that's not porous and is now made porous by the expansion of the link from oxygen from oxygen to imidazolate. So here's ZIFs. Here's another new class of materials that fundamentally is different than MOFs. And these, again, these are very stable in strong bases and in water. One of these is one of the most hydrophobic material ever known, and it's already being applied for hydrocarbon separation by BASF and made in multi-ton quantities. That's ZIF-8. So we had, in just a very short period of time, we have been able to break the record. This is a 1,000-year record held by carbon for porosity. We broke it with MOF5, and we continue to break our own records and other people's records. Right now, we held the record for porosity in 2010, and now Northwestern hold the porosity record, not by too much, but anyway, they do in terms of the surface area. So that's, once you know how to design materials, then the sky's the limit. And so now I'm going to show you another huge challenge that we've been able to address. In porous materials, the chemistry that you do in the pore has a lot to do with what can go through the pore or what can go through the opening. So if the opening is small, you can only operate on small molecules. If the opening is large, then you could use large molecules. In fact, maybe you could use proteins and other. So it's always been a challenge to open that, to open the windows or the doors that allow you to enter into the pores. And so we chose one of these MOFs to illustrate the point. And I'm not going through necessarily and explaining the challenge in great detail, but only to say that it's just has not been easy to open up the pores, because when you open them up, the structures collapse or something happens like that. But it turns out that if you choose the right structure, then they don't collapse, and in fact, you make very stable materials. So we teamed up with Fraser Stoddard, who helped us in making these links, and you can see here that the parent structure that we chose has the one phenylene unit, and our intent was to go to 2 phenylene units and 3 phenylene units and then stop. But we were successful in doing that, and so I asked the student to go to 4 phenylene units and so on, and then he did 5, and then the student couldn't go to sleep from the excitement, and we continued on to 11 phenylene units. And they're shown here. These are the opening of the parent structure, 14 angstroms by 10 angstroms. So with 2 phenylene units, you go to 20 angstroms by 16. To 3, you get 27 by 22. 4, 33 by 28. And this was essentially the previous record before we did this study. And so now you break the record with 5 phenylene units, 41 by 35. 6 phenylene units, 49 by 41, 7, 58 by 49. I'm skipping over the characterization part. 9, 72 by 61. 11, 98 by 85 angstroms. This is the largest pore opening in a porous crystal ever made. And it's made by design. All these structures are based on the parent structure. All we're doing is stretching them out to open up the pores. Within these pores, you can put very large molecules. Large molecules can pass, like vitamin B12, or this large metal organic polyhedron, or myoglobin, or even GFP. A very large protein can go into the pores, and it does not get unfolded. So now you can see where we're going with this. If you could really put proteins in there, then perhaps we can crystallize very difficult to crystallize proteins like membrane proteins and figure out the chemistries around them. So MOF chemistry really involves a variation of the inorganic-organic, expansion. We made the highest porosity materials, the largest pore opening, and we have gotten to hydrogen storage, natural gas storage, gas separations, and we've moved from selecting molecules based on size to selecting molecules also based on their electronic. Now we are playing with the interior. How do you fashion the interior of the MOF by functionalizing the organic so that we can get to carbon capture? So I'll show you that example. Water harvesting from air to make fresh water from thin air, essentially. Superacidic MOFs and catalysis. So we are moving from the frameworks being passive to the frameworks being active, meaning that they are involved in directly influencing the chemistry in the pores. So oops. Okay. All right. Well, that was the most porous, one of the most porous MOFs. It has a surface area of 10,000 meters square per gram. And that means 1 gram of this material covers an entire football field if it's unraveled to its nano level. And that's the kind of space that you have to compact gas molecules into the pores. But that's also a way to address some of the biggest challenges facing the world today, which is the fact that we have a lot of natural gas. It's 50% more cleaner than petroleum. Hydrogen is the cleanest fuel. Carbon dioxide we're trying to capture from the atmosphere and before it reaches the atmosphere. And water. Almost half of the world lives without access to fresh water. So for hydrogen, we're able to store 12 weight% in a tank at 70, in this case, at 77 Kelvin. Hydrogen is liquid at 20 Kelvin, so this is actually not bad. That means that a tank filled with MOF can store double the amount of hydrogen than a tank without the MOF, because the MOF is acting to compact the gas molecules, and therefore you can do it at warmer temperature than liquid hydrogen temperature. It's interesting enough for Mercedes to build a demonstration model based on MOFs. And the nice thing about Mercedes building demonstration models is that 80% of them end up being actually produced and sold. Natural gas is another application. Here is a tank that has no MOF, and it takes up this much methane. With MOF, in this particular MOF 519, it takes up 3 times as much. And this makes methane a commercializable material. Here's a van equipped with a MOF tank for natural gas that has been driving around Germany for 3 years. Absolutely no problem whatsoever with the MOF natural gas tank. There was only one problem, and it turned out it's the electric battery. So this is a very promising technology that is ready to launch. Carbon dioxide, for each fuel tank in your sedan, you burn about 24 kilos of petrol, and that produces per tank 85 kilograms of carbon dioxide. Okay, so the chemistry doesn't lie, it's right here. A lot of carbon dioxide is being emitted. I'm just going to show you the final result of many years of work. The idea is to capture carbon dioxide without the complication that water presents. Always carbon dioxide is present in combustion gas with water. And water almost always competes and wins over carbon dioxide in binding to porous materials. So what we did is we functionalized the pores precisely with functionalities like primary amine to actually go out there in the presence of water and pluck out carbon dioxide. Because carbon dioxide likes to bond with these amines, and it worked. So that's a MOF 74 with I'm going to skip this directly to go to the result. You can see here a MOF that is functionalized with primary amine and is in the presence of water, and the same MOF without water in the feed, and you see that the breakthrough time is exactly the same. The efficiency of the material is not altered. While a material that's not functionalized, like methyl material, you can see that the efficiency drops as you introduce water. The breakthrough times drops significantly, almost to 0. So this is the kind of precision that I'm talking about fashioning the interior of the MOF to overcome tremendous challenges. Water is another application that we are very interested in. Air contains a lot of water. It's not easy to capture water from air because it's present in small or low concentrations. But you can design a MOF that seeks water, concentrates water at low pressure. And it does so in a very sharp isotherm. And here's a MOF we call MOF 801. And this is the uptake. It shows the uptake and release of water. 80 cycles, absolutely no effect on the efficiency of the material. we did a rough calculation that if this material takes up 20% water, we have a material that takes double that, but we did the calculation for this one because we can make in kilogram quantities very quickly. But at 20% uptake, this material can deliver 50 liters of water every 30 minutes, okay? And that's for a system that has 1 meter cubed of MOF, okay? So that means that if I just have a tank filled, 1 meter cube tank filled with MOF in my home, I can basically live off water that's trapped from the air. You can imagine the ramification of this in terms of irrigation, in terms of providing water to trees in arid climate, but also we can make MOFs that work at high humidity. So, for example, in some countries, there is no fresh water, even though they have plenty of it, but it's contaminated. So this is this is a huge application, and the key feature here is that the design of the material has to be in such a way that the material can operate at a very specific pressure and have a very sharp isotherm rather than a shallow isotherm. That allows you to take the water in and fill the pores very quickly and then release them. So that's something that we are very hard working on, and we are now trying to build a demonstration model to show that this, or a small pilot, laboratory pilot, to demonstrate that this really works in real quantities. So we can scale up MOFs to multi-ton quantities with BASF, as I mentioned. They can be shaped in many different shaped bodies. And many companies around the world are researching MOFs. And the MOF literature is exploding, and so are now the patents. So those are just examples of some of the things that we have done with MOFs. I am very excited about the basic science of MOFs. What do you do after you've been able to design metal organics, and virtually any organic molecule and any inorganic can be linked and you can make a new material, so what do you do? I think there are many, many opportunities to designing the interior in such a way that it behaves exactly like a system that has a lot of chemical information, okay? And what I mean is that, I'm sorry, I'm gonna fast forward on this one to go directly to this analogy, is that if I look at the MOF backbone as the polyphosphate unit in DNA, and my functionalities as the nucleotides, I know exactly how to do this, and we've done it. We put 8 different functionalities into the pores of MOFs, covalently bound to that backbone, and they're arranged in very specific sequences, just like DNA, nucleotides in a DNA. And we find that, in fact, those systems that have these sequences perform 400% better in capturing carbon dioxide than the ones that are not mixed. So it means that I've taken a system that is crystalline, and you have units that are the same units repeating everywhere throughout the material. And now, by virtue of having these functionality sequences, I've overlaid a chemically rich information system on top of that. So it means that if I'm a molecule walking through the pores, I am seeing a unique sequence of functionalities from the beginning of the particle to the end. And so it means that we can design sequences that code for very specific properties. So instead of just using the whole material to do one operation, now you can have a material that does many different operations and codes for very specific properties. It means also that molecules can now float into the pore and move in a circuitry type of arrangement rather than bumping around in Brownian motion type of arrangement. So we're going to create directionality in how molecules diffuse through the pores, something that you can't do any other way. The other, I think, facet of this that we did not expect, except at Berkeley we have great students and they diffuse around various groups. And in my group, I have a couple of these students, and they talk to everybody. But what turns out that we can actually address what I call the functionalization problem. Nanocrystals can be easily functionalized, but you can't place a functionality where you want it. And so why not use a MOF as a complex functionality? And now, since I can control the size of the links and the functionality of the links, I can control exactly where they should go on the surface of the nanocrystal. And so in one shot, we are able to really impact on the nanocrystal, inorganic nanocrystal world by wrapping. In this case, you may not see the center of this, but it has platinum nanoparticle wrapped by a MOF nanocrystal. So it means all the chemistry that I can do with the MOF that I just showed you can be now applied to this MOF nanocrystal to impact on the chemistry of that platinum catalyst. That platinum catalyst now, enclosed within the MOF, behaves very differently in terms of selectivity and in terms of the temperature that it operates on. So it operates at 150 degrees in this case instead of 250, and we see selectivities that are more towards cyclic products rather than the other products in this reaction. So that's very exciting, because it means that we are stabilizing certain intermediates by virtue of the MOF being wrapped around the catalyst. And the catalyst, after you use it, it looks exactly the same as before. And so this is something we're very, very excited about, and especially in terms of exploration with KEX through our center. You can expand the pores and see that the selectivities change and so on. This has not been possible before. You can change the acidity of the links and then look at how it impacts the selectivity of the products. These are for a catalyst like platinum over silica, which has been used for many, many years. Now with one shot, we can actually change its chemistry and go to more favored selectivities. Or we could also impact on the homogeneous catalysis. In homogeneous catalysis, you do step-by-step sequential catalysis. Why not take 3 catalysts that carry out a transformation like this and put it in the pores so that the 3 catalysts can operate in a tandem or cascading way? So that's an idea that we are developing now. Finally, I want to close by sharing with you something that is inspiring me these days. I'm very, very excited about this. In all the chemistry that I presented to you, and in all the chemistry that chemists have ever done, the linking of molecules has always been through covalent bonds, or through metal ligand bonds, or through hydrogen bonds, but never really beyond molecules. Never have we been able to build extended structure based on mechanical bonds. Okay? What do I mean by that? I mean by interlocking a circular molecule with another molecule physically and not chemically. If I could do that, then I would change the properties of materials. I could make polymers be more deformable, and they can last a long time. I could make materials that are highly dynamic, but yet very have survivability much, much higher than they would be. So it means that I can make materials that no matter how much you bend them and so on, they don't break. Okay? And that's because you're moving around within this interlocking rather than breaking covalent bonds and creating defects in your structure. But how do you do this? How do you get nature to do this? This is an example of how it might be done. This is an example of a molecule that could be made by interlock, or an extended structure by interlocking rings. And this is an idea that we're working on. I'm going to just put it here out there to let you know that we are beginning a field that is much, much larger than MOFs and ZIFs. It really is much larger. And the materials that we are doing will transform the materials world because they're going to be dynamic. Okay, we're going to be able to stretch these things and bring them down to smaller size without breaking them. And once you know how to make one weave or one ring, you can have a cluster of rings interlock with another cluster of rings. Or you could have chains that are interlocking, as you can see here. Or weaves like this. Okay, this could be one chain, another chain, and so on. And this sounds very hard, but it actually is not hard because we figured out how to make the crossing. Once you know how to make this crossing, then the whole thing can be duplicated. Now imagine a world where one chain is one composition and the other chain is another composition. So one is silica and the other one is organic. What kind of material will we make? What kind of properties will they have? Or maybe your chain is actually a braid. It's actually made from, and all of these are not just pictures. They are actually, we have synthetic strategies to make all of these. This is what you will see in future. But this is no stranger to the natural world. So already, the natural world already uses these interlocking rings. In this case, this is a virus. Interlocked, made of 6 proteins that are hydrogen bonded, okay? And they are interlocking to make an extended, or to make the capsid of the virus. And this virus, as you know, when it has stuff in it, it's expanded, and when it doesn't, it collapses, or it shrinks, and it's reversible, okay? But in our world, these will be linked through covalent interaction, but mechanically interlocked. So they will operate under many different conditions. So over the years, we have conceived and been able to make MOFs, COFs, and ZIFs, and so on, and CATs, and MTV MOFs, and nano MOFs, and weaved nets. And each one of these has really sprung new kind of applications and address major challenges in chemistry, as well as applications. So we really have created a new kind of chemistry. I call it reticular chemistry, and that's the control of the strong bond. But nature, again, is very beautiful, and just historically, materials have been made from one kind of building unit, or 2 kind of building units, or 3 kind of building units. But what about 4, 5, 6, 7, 8, 9? Okay, this I call is the materials beyond. There is more to come than we have ever been able to imagine. And that's going to be enabled by the fact that we are able to link things through strong bonds, as we have done with MOFs. The fact that MOFs can be easily made really has inspired a lot of young people. These are German kids, but I know it has inspired a lot of young people around the world. And this meant that it's very easy for us to start centers around the world to provide, I would say, a laboratory for young minds to learn how to do research. Just like when I was growing up and I went to the library and I was intrigued and captivated by those drawings, those students can now go into their laboratory and mix chemicals together to make new materials in the way that I've been describing. This is a very fulfilling kind of work, and it is probably much more important than anything that I would ever do, and that is the impact that you make on inspiring young scholars. And so I want to acknowledge my group and thank you again for your gracious hospitality, for nominating me for this award, and certainly for your friendship. I look forward to working further with you.